Well, hello friends. Welcome back to the program. Today we are going to hack the system once again, and it's going to be a kernel exploit to get root access. And I found a bug in our munmap syscall implementation. So let me first talk a little bit about munmap and partial unmapping. So normally when you memory map a region, say that you call mmap with, you pass in null putter because you don't care where it goes, and then some number of pages, say that you want 4 pages, right? And then the rest of the arguments. So what you end up getting in the Serenity kernel is a pointer to a region of memory. So you get a region that has 4 individual pages. And this is all cool. And then say that later you call munmap with, well, let's store that somewhere, putter and 4 page size. And of course, then this region will go away. So it doesn't exist anymore. But what happens if you call munmap with another size, not the full size, but just a part of the memory range? So what happens then is that we have to split that range into 1 or 2 new regions. So say, for example, that you call munmap with 3 pages. Then what ends up happening is you get a region that looks like this in the end instead, and the last page is carved out. Likewise, if you were to call munmap with putter plus page size and 3 times page size, you would get a region that has 0, 1, 1, 2, and 3. Sorry. So these are pretty understandable. And then we also have the final case, which is if you remove a part in the middle of the region, and then what happens is you get 2 regions. So in this case, one region with page 0, and another region with pages 2 and 3, but page 1 is gone. So this is standard Unix POSIX stuff, right? And it's kind of interesting because the specification doesn't really talk about like how this is implemented internally, but it says that you are allowed to munmap right in the middle of a region that you previously mmapped. So in Serenity, this is how we implement it, that we have these region objects. And I suspect that other Unixes do something similar, although I haven't looked at them. Anyway, the bug today comes from how we create these new regions when we get rid of an old one. So the code path that deals with full unmapping, like you unmap the entire range that you mmapped, that code path is fine. But in the case where you're doing a partial munmap, we have a problem. So I'll show you what the problem is. In sys munmap. So the munmap syscall is pretty easy to understand. So we start by searching for a whole region that, if there happens to be a memory region in this process that is the entire region that you asked to unmap, then that is very easy. So we can just deallocate that region and success, right? But if we're not so lucky to find a whole region, then we go and look for one of our regions that contains the range that you want to unmap. And if we find such a range, then we split that region around the range that you are unmapping, and then we deallocate the old whole region that you're unmapping in the middle of, and then we take these new regions that you got from split region around range, and we map those instead. So basically, split region around range returns a vector of replacement regions. And It can be 1 or 2 replacements depending on if you're chopping out, at the start of this region, at the end of the region, or somewhere in the middle. So if you're at the start or the end, you just get 1 replacement region, but if you're in the middle, you get 2 replacement regions. So far, so good. Now, the bug happens in split region around range, and specifically in the construction of these replacement regions. So split region around range has this helper called make replacement region, which calls allocate split region. And what allocate split region does is that it takes a source region and then carves out a range of that region and gives you back a new region object that is backed by the same exact physical memory as the old region, but only covers a slice of it. So that's what this does. And the replacement region, the new region, is constructed by calling region create user accessible. And we sort of pass in the range and the VM object of the source region and blah, blah, blah. And everything here looks good, except the bug is actually super subtle. So the issue is that region create user accessible has a few more arguments that we're not passing because they have default values. So there's cacheable, which defaults to true, and shared, which defaults to false. And since we're not passing them, they're going to be true and false. So when you are creating these replacement regions, they're always going to be cacheable and never going to be shared. And that can be a huge problem if your source region is shared, because this effectively allows you to take a shared region and chop it up into 1 or 2 private regions. And then once you have a private region, that allows you to bypass certain permission and sanity checks that apply to shared regions. And that's something that we're going to be exploiting today. But I first just wanted to give you this sort of overview of partial unmapping, and then to show you the bug here. So of course the fix for the bug is going to be to simply propagate the cacheable and the shared flags from the source region when constructing these replacement regions. But before we actually do the fix, let's exploit the problem. So this turns out to be extremely exploitable because the shared flag is used when we do mprotect. So let me show you how. In mprotect, which is a system call that you use to change the permissions on a range of memory that you have previously unmapped. And you can use it to switch the readable, writable, and executable flags of a range of memory. And in fact, it has the same behavior as munmap, that if you call it on a slice of an unmapped area, then we also have to split it into parts potentially, because in our case, in the Serenity kernel implementation, we have a strict sort of invariant that each region has a set of permissions, and you can't have subregions with different sets of permissions. So if you want to have a range of memory with different permissions than his neighbors, then you just need to put him in his own region. And for that reason, mprotect also needs to split. But that's all just details right now. But the important thing is when you call mprotect on something that is backed by an inode, so it's backed by a file, not just anonymous RAM, then we call this thing called validate inode mmap prot. And this is where we check that the new protections that you want to set on this memory range actually make sense for the underlying file. And this is so that you can't just like go and mmap like a random binary in /bin, and then unprotect it writable, and then write to it, unless you are root, right? Because you don't have write access to /bin binaries. However, we only check this type of stuff if it's a shared mapping, because you can map say bin sh writable if you like, as long as it's a private mapping. If you make a private mapping of some random thing, you can do whatever you want to it, because your changes are private. So by definition, they're not visible to other processes, and they are not written back to disk. They're just your private copy. You're free to do what you like. But where does this map shared flag come from that causes us to check this? It is passed in here as a parameter to validate inode unmap prot. And validate inode unmap prot is called an unprotect. And wouldn't you know it, we pass in the region is shared flag. So that is the same flag that's always false after you have split a region. So what does that mean? It means that we can take a memory region for something that is inode backed and shared and read-only, and then we can trick the kernel into making that region appear private, and then we can unprotect it bypassing these checks here and map it writable. And then we should be able to write to a file that we're not supposed to be able to write to. And in fact, because of physical memory sharing in the system, if we write to a dynamic library in our process that's also mapped by other processes, those changes will be reflected in the memory space of those other processes. So we can effectively overwrite library code in other running programs. But I think that's enough about the theory of why this will work. So let's go and actually write an exploit for it. Of course, we make a haxx0ring. That's the obligatory name. And now we are going to type this exploit out. I feel like I laid it out pretty well. So the way we're going to attack this is, right now, I can't SU because I don't know the password, right? But wouldn't it be cool if we could just patch SU somehow so that it allows any password to come through, and it just always says, yes, that is a valid password. So it turns out that we can actually do that, because if we just look at SU here when it's asking for the password. Oh, we can't look at it in my unprivileged system monitor. But okay, so instead, let's go look at the code for SU. So we know that SU verifies my credentials, or the provided credentials, by calling core account authenticate. And authenticate is a simple function that takes a password and then returns true if the password is correct for the account you're trying to authenticate as. So we can just patch this function to always return true. And this function is in libcore, which basically all we need to do is to make a haxx program that links with libcore and then finds libcore in its own memory space and then patches this function. And then actually makes that memory writable momentarily by tricking the kernel into marking that region writable or private. And then we patch authenticate so that it always returns true. And then we SU and authenticate will return true, whatever we type. this is the plan. So let's make it. Oh, and the way that we're going to find the libcore address in our memory space is we're just going to use the proc file system for that. So if we look at this shell, for example, we have proc 25 VM, and it's JSON, so it's a very computer-friendly format. It's just a JSON array with a bunch of objects, each object representing one memory region. And if we look for libcore, we can find libcore text right here. So we need an object with this name. Then we have the address and the size of libcore in the process, and then we can do the unmap partial trick, and then patch the authenticate function, and then we should just be able to run SU and it should work. Okay, so step one. Let's open the VM file. Okay, so we're opening our own proc file entry, and if file is error, then return 1. Okay, and then JSON is file value read all. Okay, and then we're gonna loop over all of the objects in this array. So JSON value as array, values, and then these are gonna be JSON objects. So object is value as object. Okay. Object get. We had name, address, and size of each thing. And the address and size are actually U32, so we'll just convert those. And let's see, so then we're looking for libcore. So let me just write out what we're finding here so we can see. Region at pointer size this and that, name, address, size, right? Okay, so this should print everything out. Let's test it. Cool. So this is everything that's mapped into the haxx memory space. And we can see that we're using libcore here. So we have a libcore mapped in our memory space. So it's this name right here, libcore.so text. So we can just look for that one. So if name is libcore.so text, that's it, right? Yeah, so when we find that region, then we want to unmap part of it and then overwrite part of it. So libcore base is going to be, I mean, we already have the address, so it's just a U8 pointer from the address. And then we need to do the unmap trick. So unmap. What do we unmap? Maybe let's unmap like the end of it, the tail end of it. Libcore base plus size minus page size. So like we just unmapped the last page of libcore. Probably harmless. Then I guess we need, this is a man. Cool. Okay, and then, so once we do this, by the way, this should cause our libcore mapping to go from shared to private. So maybe we should verify that that actually works first. So we'll sleep before doing the munmap, and we can take a look at the state. Okay, so we found the region. So this is before doing anything. Naughty. We have libcore is right here, and we can see that it is shared. So everything is looking good, right? It's shared, and it is backed by a shared inode VM object. And this is actually important because a shared inode VM object is a kernel virtual memory object class that represents an object that is shared by, it's shared globally. So anybody else who has a shared inode VM object for that same file will see any changes made because they have the same, they share memory, right? It's a memory usage optimization. Every program doesn't have its own unique copy of all of its shared libraries. Instead, they are just shared globally because they're not expected to get altered. But now we're going to try to alter them. So if we do this and sleep after we've done the munmap, so we munmap the very last page of libcore and then go to sleep. Then what can we find? Haxx. I really need to fix this thing so that the selection doesn't disappear all the time. But unrelated. So now we can see here that libcore is still a shared inode VM object, but the shared bit, the S here, is missing. You can see an S up here on libcrypto, but not on libcore. So we have successfully removed the shared flag from that region. So this means that we should be able to protect it and change the permissions. Size, minus page size, of course, because we have removed one page. And then prot read, prot write. So now we're making it writable. And then of course we can't actually make it writable and executable at the same time because the kernel doesn't let us, but we can make it only writable. This also reminds me that we need to implement proper wx x, but because that's not working right at the moment, so that would be an additional defense here, I suppose. But anyway, that's something we also need to take care of later. So many mitigations that we need to add. So yeah, so now we're making that memory writable, and then we just need to figure out where is the that authenticate function. So userland libraries libcore.so less, boom. Okay, and then we are looking for authenticate, and here she is. And we'll just skip through the end and look at where we return. So returning here, and the return value is an EAX. So we can see here that EAX is set with a setcc instruction. It's these 3 bytes right here. So it's setting, based on the result of this test here, it's setting it to whatever the 0 flag is, but we can just patch this instruction with something else. So we're at offset 12D1F. So make like a haxx putter. And that would be libcore base plus this offset, and then haxx0ring. So what are we gonna put here instead? I guess we want to return true, which means that we just need to set AL to 1, right? So we just want to set it to mod AL1, right? So we need B001, and we actually have 3 bytes to fill, but then we can just put an op. So just lead with an op, and then patch in the mov instruction. So mov AL1 op. Cool. Okay. All right, let's, oh, now we're totally, everything is totally messy. Getting assertions in the dynamic loader. Okay, I don't know what that's about. Seems like the system does not like being in this state at all. Dynamic loader. Oh, did I just mess something up really badly? Okay, so then it will fail to map. I guess the new process is trying to mmap libcore, and then it fails for some reason. I guess we can say here why it fails. Wait, why does that fail? Okay, blah, blah, blah. Permission denied. Okay. Oh, wait. I guess because now there exists a writable mapping to libcore, so then I start a new process and it tries to map libcore executable, and then it notices, hey, wait a minute. This library is mapped writable by somebody. I can't just let you execute that. So it tries and fails, sort of, to protect us against modification. I think that's what it is. So let's just check if that's it. In sysenmmap, we have validate inode mmap prod, which looks at it's a shared mapping, and it's not necessarily writable, but we look here if we want to map it prod exec, and if so, if it has writable mappings, then we fail. Yeah, so it's this check right here. So we're starting a new program. It's trying to map libcore prod exec, and because we have a writable mapping to it, then it just says no, you can't map this prod exec. Okay, but we can easily fix that by just getting rid of the mapping after we have, or actually just remapping it without the writable bit right after patching it. So we're going to have haxx0ring it, right? Now everything should be back to normal. Nobody knows what hit them, and core account authenticate has been patched. So we, haxx, and su, press enter, just works. Hello, just works. Any password is good enough because we hacked it. So yeah, that was really straightforward, but pretty neat. So yeah, so what have we really done here? So we iterate through all of the memory regions in the haxx process itself. So he just looks in his own proc file entry and locates the information about the libcore mapping in the haxx process. And then we take that pointer, which is a pointer in our own memory space, which has been mmapped there by the dynamic loader. And we go and we say, okay, so unmap the very last page in this mapping. And that causes the munmap splitting logic to kick in. So this thing that we talked about, right? Because we're unmapping the very last page. So in this case right here, we're cutting off a page, and the replacement region that is constructed does not preserve the shared flag. So it goes from being a shared mapping to a private mapping, despite not moving from a shared inode VM object to a private inode VM object. And so it retains the shared inode VM object, but we can now bypass the mprotect checks. So we map the entire libcore library as not executable but writable instead. We patch the authenticate function with a return true, essentially. And then we finally remap it executable so that nobody suspects anything. And then we are done. So yeah, that's basically it. I guess we could even like exec gulp bin su here, just to really drive the point home. Haxx0ring, enter any password to become a root. Let's make a cool looking thing here. Gotta get better at making cool looking exploits. We'll at least put some colors and stuff, right? Da-da-da-da-da. Nice. That's pretty cool. Okay, so that was the exploit part. Now, of course, because we are responsible operating system developers, not just haxors, we are going to patch this issue. So let's go and fix the replacement region construction function in the munmap logic here. So call split region around range, allocate split region, right? So this boy right here calls region create user accessible. So he's missing these arguments, but I don't want to have this bug again, right? So let's make sure that we always have to pass in these flags at least, so that we can't shoot ourselves in the foot with these default arguments. So let's just remove them both. Or actually this one is kernel only, so let's not touch that one. And cacheable is less of an issue. That's just gonna give you bad performance if you set the wrong thing. But for shared, let's make sure that we always have to pass it. And then we'll notice some red over here actually telling us that something has broken. So presumably we're just missing some things here. So this is when we're cloning a region. Apparently we're also not passing these in. So on fork, we are not cloning the cacheable and shared flags, although we are in the mshared branch here, so we know that that's actually always true. But even so, like, it seems like we can just pass them along. Doesn't hurt anybody. Cacheable and shared. Okay. And let's see what else breaks if we just build. Silly default arguments. Process. Okay, so source region is cacheable and source region is shared. It must be preserved. And we also have a call. Where is it? Here, create user accessible. What is this? Process allocate region. who calls that. I guess nobody who calls this expects us to create a shared thing, because it doesn't have a shared input flag, and we are always constructing a new VM object. So in this case, like it's implied private, but I guess we can just explicitly provide those instead. And then also in memory manager. So it turns out that there were quite a few places where we were using these defaults. Likewise here, allocate kernel region with VM object, and then it should be shared false. So we're creating a user accessible kernel region. I don't even remember what we used that for. I think it's maybe for the signal trampolines or something like that. Which are technically shared, but I guess we shouldn't map them as shared. Yeah, I'm not completely sure about that. Like, in general, like the fact that we have a way to create a user accessible kernel region seems to me like a design mistake, and we should probably look into not supporting that. But first we need to figure out what it's for, and I'm not going to dig into that hole right now. Okay, but now we've built, and of course now this just fails with permission denied on mprotect, because you can't go and change the permissions of this region because it's mapped shared. So that's cool. So that's our fix here to get rid of the default flags, pass them in explicitly, and make sure that we don't allow this exploit. Kernel. Always fix bug in memory unmap region splitting where shared flag was not preserved, or let's say unmap region splitting did not preserve shared flag. This was exploitable since the shared flag is used to shared flag determines whether inode permission checks are applied in mprotect. Yeah. The bug was pretty hard to spot due to default arguments being used instead. This patch removes the default arguments to make explicit at each call site what's being constructed, what's being done. Yeah. Okay, so that's good, and maybe we can add like a little bit of sanity check, like the fact that we were able to get out of sync with like a shared or non-shared region, and then we have this shared or private inode VM object. So the inode VM object is a base class, and then it has two subclasses, the shared inode VM object and the private inode VM object. So we can actually, the fact that we were able to get out of sync, so we had a private region with a shared inode VM object, I feel like we could assert that somewhere, that we don't get out of sync with those things, even though it's like, it's a little bit weird that their shared flag is sort of split like that. But we can most definitely assert that it is coherent. So what do we do? I guess we can have like just thinking, what are all of the VM objects we have? We have anonymous, inode, and contiguous. And we could say that like, what if we had a question you could ask it, like allows sharing, or can be, or allows sharing is kind of good. I was thinking maybe shared, can be shared, allows sharing, can, I don't know, something like that. Let's call it can be shared. And it will be true by default, but private inode VM object will say no. Wait, does that make sense though? That doesn't quite make sense, because if you fork a process that has a private inode VM object, now both the child and the parent have that same thing shared. Okay, so that doesn't quite make sense. Let's see. The thing that we want to catch is if you have a private region on top of a shared inode VM object. So it's a shared inode VM object that has the precarious situation, right? So he's the one who needs to say, oh no, not with me. I do not consent to this. So maybe we should just look for is shared inode then. I was thinking we could generalize this, but maybe it's not necessary. So where do we do that? I guess we can do it in like region map. So when you're mapping a region, or maybe even when you construct a region, although can you change the shared flag after the fact? Or sort of. That's a little bit hairy. Okay. Okay. So let's do it when you map the region for now, and maybe there's a better place to do this. I just want to have a sanity check somewhere so that we don't lose this. So we'll do that here. So if it's a non-shared region, and the VM object is shared inode, we should assert that it's not a shared inode, right? Yeah. Because this would be a big no-no. So then the kernel will just panic if you get into that state, which we immediately did because I didn't think something through. Why is that happening? Load elf object. Allocate kernel region with VM object. Okay. Load elf object. Oh, I guess because kernel regions are always private. Okay, let's back up. So let's say if this is user accessible and shared. User accessible and private. Yeah, so we can allow the kernel to do it. For now. Yeah, that's okay. But fix me, maybe move the sanity check to a better place. Find a better sanity check. Yeah, because I'm not sure if that's like the best place for it, but let's verify that it at least would panic the kernel. So let's go back to having the bug. So instead of passing in is shared, we'll always pass false. So bring back the bug, and then we'll run our hacks. And yeah, so now our kernel asserts here instead if we get into this bad state. We shouldn't get into this bad state, but I think asserting or panicking the kernel is better than getting rooted. So there's that offensive programming strategy for you. So let's take this. No, not gay. Get gap. That's what I wanted. Okay. Kernel assert if assert on user on attempt to map private region backed by shared inode. Yeah. If we find ourselves with a non-shared region backed by a shared inode VM object, there's a non-shared region, user accessible non-shared region backed by a shared inode VM object. That's pretty bad news, so let's just panic and not allow ourselves, let's just panic the kernel instead of getting abused. Yeah, and then there might be a better place for this kind of check. So I've added a fix me about thinking or putting more thought into that. Yeah, okay. So, oh, wait. Yeah, that's good. I was just thinking I was not committing the bug back into the kernel, right? So haxx no longer works. We have thwarted the exploit. We have removed the default argument. We've added an assertion to region map that checks for this invalid state. So I think we're basically done here for today. So something going forward that I think we need to improve is wx XOR x, which basically means we need to get to a place where something that has ever been mapped executable in a process cannot then later be mapped writable, and vice versa. But currently we don't have sufficient checks for that, and that's something that we need to improve. And if anybody knows any other relevant mitigations that would help against this particular thing or this sort of thing, please let me know. I'm always interested in improving system security, and of course I'm learning all of this as I go. You can tell that I'm not super comfortable with exploitation, although I think I'm getting better. And this is really interesting stuff. So this is the end of the video. I hope that you saw something interesting. Thank you all for watching and for hanging out. I think maybe it's time to do some regular OS hacking soon. I've been doing so many exploits in a row now. I need to do some regular building stuff, but it was nice to do this one. So I hope you enjoyed, and I will see you all next time. Bye.